All right, thank you all for being here. So my name is Franco. I'm a blockchain engineer at Nethermind. I'll be discussing a little bit about Web2 identities, zero-knowledge proofs, and account abstraction. So basically how we can introduce the Web2 identities into Ethereum, but in a private way. So the main questions I want to answer here are, well, why is Web2 identity-based onboarding interesting? So using the same identities people already use for their other platforms, which are usually social login based. How to establish a protocol for privacy-preserving identities based on Web2 identities through ZK, and how to integrate all of that, how to glue this all together into Ethereum through account abstraction. So, and finally, what are the open research points as well? So what are the details? And as you probably know, for, well, everything else, the devil is in the details. So it's important to discuss those. So Web3 accounts add friction. That's the summary of this whole talk, or why it's interesting. Not that it's one solution in terms of Web3 accounts, but I'm talking about the usual wallet creation and management workflow. So a user that is getting on board into Web3, they have to choose a network to interact with first. Then they have to pick a compatible wallet app. They have a plethora of options, different functionalities, different securities. Then they have to generate and store a passphrase. Then they have to make a password. Then they have to set up an account. They have to fund it. Sometimes they have to deploy an account contract. So they have to do all of that before their first transaction. And that is an actual issue, right? Because Web2 is simpler. And people are used to the simplicity of Web2. So we, as crypto-native people, mostly, we are used to this complexity, and it may not seem complicated to us, but this is a bias. This is a clear bias. And it's very hard to compete when a Web2 application can just integrate with a Web2 identity through social login. So, for example, you have login with any social network you might want. You go there to your API, you integrate this into your authentication process, and you're done, right? People can just do a click, and now they're into your application. So comparing this to Web3, where you have to do all of these extra steps, you have to go through all of these complexities in order to get into contact with a Web3 application. Like, this is not a fair fight, per se. But we have different ideas. We have different purposes. Still, can't we do something similar, right? One other way of explaining like this figure is through a meme, right? You have like Web2 onboarding, which is very simple, and then you have Web3 onboarding, which is, well, a total mental gymnastics. And if you think that it's not a mental gymnastics in any sense, you're probably the guy in the last picture over there, right? You're already running over the fire, so nothing is hard to you anymore. But the people that are on the start, they feel it's hard. And if you talk to people that don't really come into contact with Web3 that much, they will probably confirm that vision for you. So we need simpler onboarding. Three main arguments for that. One of them is that an account is a means to an end. People don't create an account because they want to create an account. People create an account because they want to interact with a protocol. They want to use our application. They want to use DeFi. They want to do whatever. And the more friction this initial contact brings, the more likely they're just going to think, meh, I'm not going to do this anymore, right? Second argument, there's a lot to learn, right? The learning curve is already very, very steep. And if you can make this a little bit smoother, then it's better, right? If you can delegate or you can delay complexities for later on, that's better for the user. They can worry about whatever later, and they just get into contact with your application in the first place. They find it very nice. They find it very interesting. And then they worry about all the other complexities. And actually, the most important argument of them is that familiarity is important. And as much as we know, or that we may think that, for example, keeping our private key stored in our devices is the safest thing to do, this is not the usual authentication flow, right? And people are used to trusting their usual authentication flows. In their defense mechanism, their internal thoughts process is, well, if it's not the same thing, then it's probably sketchy, right? And it's strange. And we're usually dealing with money. So this adds up to like, this is sketchy, and I don't want to put my money into it. And that is what we would like to solve. But we would like to solve it in the Web3 way, right? We don't want to just do whatever. So can we offer a similar experience? How can we do that? And is there any existing solution? So there are, actually. So you have some account or some wallet solutions that already offer social login for different networks. You can go there, you can use your credentials. But it's important to discuss this in a deeper sense because this requires off-chain interaction. And anything that requires off-chain interaction means, well, additional complexity, trust assumptions, usually a custom protocol. So you have to think about all these things, right? You have to think, well, is there an intermediary? Are you going to trust someone to deal with this information? You're going to pass it, and then they are going to relay this to someone else? Who is the oracle if you're going to get external data? And how are you going to prove that the oracle is right? What are the trust assumptions in general? This affects basically all of the questions. Is it sufficiently private? That's a very good question as well, because usually we don't really want to link our accounts to our real identities. And using social logins for that is, well, you would be linking them. And even more importantly so, is it compatible or is it easy to integrate with existing tooling? Because if it's not easy, then it's not going to be to receive development. And not receiving development means, well, dying. So the state of the art in terms of these solutions is called ZK login. It's a solution that was brought by Sui Network. They use it in their network, but it's a general, it's more of a protocol thing. The idea there is that you are sending transactions from a Sui address using an OAuth credential, but you're not revealing the OAuth credential. So here comes ZK, basically, right? You generate your JWT, which is your token for authentication into your social login provider. And you generate a ZKP proving that JWT is valid. And then you submit the transaction and the zero-knowledge proof to Sui, which will then verify it and will attest that your identity is correct. It has some extra steps. This is a very simplified process, and I will explain a little bit more how it's more complicated. So first of all, here's an OpenID Connect payload. This is a JSON, and the idea of it is that it resembles an ID card. So you have your sub, which is your subject, like your username. You have your issuer, which is whoever emitted that. You have your audience, which is who's going to receive that. And you get all of this information, and you encode it in a JWT, which I was talking about. So you have a header, you have a payload, you have a signature. The header is the information or the metadata on the signature. The payload is what you see below, what you see above. And the signature is the attestation from your OpenID provider that your identity is correct. So the way that the way that this could be integrated into a blockchain environment as well. Okay, we need to put this into our chain, and we need to verify it. But while we're doing that, we're exposing the user's identity. So if you're sending this and you're processing it publicly, the user's identity is there. That's where the ZK proof comes from. So let's verify through a ZK proof, right? But you have two main problems with that. One of them, proofs are expensive. Why is that? Because, well, as it's kind of a bias in ZK applications, you can't always tailor your application towards ZK. In this case, normally OpenID providers use RSA and SHA-2 for the signing process. And SHA-2 specifically is not ZK friendly. So it's very hard or very heavy. You require a very beefy machine to prove that. And there's another problem as well, because while the JWT on itself is already a stable identifier, it's already mentioning who you are, we don't want to reveal the JWT. So we need some other identifier, which is private, but it's also stable. So you have some other non-identifiable identifier that is not linked to your actual Web2 identity. How does everything work in terms of that? Well, one of the breakthroughs in ZK login is it actually leverages the OpenID payload's nonce, which is a replay attack prevention field, as a metadata field. So the idea with replay attack prevention is you don't want people to use the same nonce. But their thought on that was very smart. Is, OK, you can embed data on that. So the nonce in the ZK login protocol is not a replay attack prevention field, per se. It's actually consists of an ephemeral public key, an expiration epoch, and some randomness for unlinkability. The important part here is the ephemeral public key. Why is that? Because, well, when you do this, you're actually making it so the JWT is now a digital certificate, right? So you're basically making the OpenID provider attest that you're going to then use a certain public or a certain key pair to sign your transactions. And this has two main uses, and it actually solves a little bit of the first problem. Well, first one of them is that multiple operations can be signed with the same ephemeral key. The reason for that is that now your zero knowledge proof is not actually proving, it's not tied to your transaction. It's tied to your ephemeral public key. And it's saying, you're going to use this key to sign your transactions. So you can use one proof to change or to your ephemeral key, and then you can sign multiple transactions. That is very interesting, and that's very efficient, especially because I was talking, this requires a very beefy machine, and this takes a lot of time. And this also solves a little bit of the problem of offloading proving. Well, if we can't do this in consumer hardware that much, if it's that heavy in terms of non-ZK friendly processes, if we have the ephemeral key embedded into it, this means that we can offload proving to an external server, and because it won't know our private key or our ephemeral private key, it won't be able to make transactions on our name. So it's only proving the validity, and it's only proving that we're going to change this to this public key, but the private key is still ours. So that makes things a lot safer and a lot easier to handle. But the second problem is still not solved. So we have an efficient way of dealing with this, and we have our ephemeral keys there working, but we still don't have a stable way of identifying users between sessions. So we need to have a user ID that is not linkable to your actual user ID from your Web2 identity. And the way that this is done is that ZK login actually defines a stable identifier based on the provider ID, which is one of the fields in the OpenID payload, and the hash of a key claim, an audience, and a user-chosen salt. Digesting this a little bit, the idea here is that you're making it so now you have an address seed, which is based on your subject, or this is only a choice, actually. It could be, for example, email, and a specific salt, and you're only revealing your address seed to the verifier. So it is stable because it depends on the subject, but it's not linkable to your user ID specifically because you have what's called their salt, right? You're mixing some randomness or some user-chosen value there, which means even if the user knows all of the accounts or tries to brute force their way into knowing your identity through the provider ID and the audience, they can't really know it because they don't know the salt. But this actually this changes the problem a little bit. This brings us to an easier problem, but a different one. Because, well, as much as adding a salt brings in linkability between address seed and key claim, so now you have a stable identifier which is not linked to your actual identity or to your stable identifier from your JWT. And also, it allows multiple accounts, by the way, right? Because you can choose different salts and have different accounts. You have to manage the salt somehow. So you can't just simply throw this around. And it's actually worse than that because, well, you could say, OK, let's make the user handle the salt, right? The problem with making the user handle the salt is that we're back to the first problem. If we don't want the user to handle a private key, why would we want them to handle a salt? So inconvenient. But we'll talk about this in our open questions. So in a summary, how does all this mess work? So the user first generates an ephemeral key pair. This can be done locally. It builds the nonce and requests a JWT. So now it has the attestation from your OpenID provider that, that is going to be using that ephemeral key to sign the later transactions. It retrieves or generates a salt, then computes their stable ID, proves the JWT through an external prover, because, as I mentioned, this requires a very beefy machine. And remember the ephemeral key pair, right? We can't trust the prover somehow because it won't be able to know our ephemeral private key. And it sends this public proof data and the transaction or the transactions as a payload to your chain. So with all of these masks, the takeaway here is that, OK, now you have most of the problems solved. We are hiding some of them in the salt service, for example, but you have a stable identifier that is not linked to your actual identity, and you have a way of being efficient in terms of these zero-knowledge proofs. Verification process is, well, it's simpler, though it also has a caveat. So first, you need to know what the key from your OpenID provider is. You get their JW key, their keychain, and you try to match it with your JWT signature. This needs to be Oracle-based, because these keys can change. So that's also an interesting problem. But keeping that aside, then you verify the proof expiration time, just knowing if that generation is not expired yet in terms of the protocol. Then you verify the zero-knowledge proof, which means, well, your stable identifier is correct, your nonce is correct, and the JWT verifies the signature is correct, but not revealing the JWT itself. And then you verify the ephemeral signatures. That's basically it. So why don't we do something similar on Ethereum? And that is actually not that much of a stretch. I mean, I know this is a little bit complicated in terms of all the inner workings, but if we just put, where was SUI, Ethereum, and we are now dealing with smart contracts, so we are pushing this data into smart contract, it's using a JWK Oracle, it's using a ZKP verifier, it can just verify the ZKP and do the operations for you. And yes, we actually have most of what we need, right? So we think, oh, well, proving could be based on a prover service as well. Verifying zero-knowledge proofs in smart contracts is also commonplace. There's nothing really too much special about proving system or anything. Using fixed JWKs is OK as a first approach as well. Like, let's keep that aside for a while. And we don't actually need a protocol change to allow accounts that use this, right? SUI has this as a first-class citizen, but we have account abstraction. So one of the most obvious use cases of account abstraction is, well, alternative transaction payloads. You're embedding additional data into your operations. And in this case, we can just say, OK, we're going to embed a zero-knowledge proof. So instead of saying that our signature for this smart account is, well, an CDSA signature or something, we're saying, OK, this can have an ephemeral signature. This has an ephemeral signature, and this can also have a zero-knowledge proof. And if there is such a thing, then we update the ephemeral key, and we process everything. So an example design of that would be, well, we use an account abstraction standard. We initialize it through a ZK login proof, so now we have our stable identifier. We define our signature as an ephemeral signature plus an optional ZK login proof that will change this ephemeral key. This is also, well, as we mentioned, this is gas efficient because we have multiple operations per proof, and we have a CDSA signatures. So both things get cheap, especially if you're doing multiple operations. We could even use some alternative solutions for verification if you really wanted to. The same latency as ZK login, right? You have like a few seconds for each transaction because of proving, which is different. Like if it was consumer hardware, not a proving service, it would be minutes or tens of minutes. It's compatible in general with EVM networks, okay, because of the account abstraction standard. The problem is we're verifying a ZK proof, so this has some caveats, some details to take care of. Some networks may deal with this a little bit differently. Integrating in an account abstraction wallet should not be complex, right? Because you're already using a CDSA, and you're just making an extra step to change this ephemeral public key. So it's like you're going to add a little bit of code there. It's not too much. And it also allows using any other account abstraction building block, which is where things get more interesting, right? We're joining the account abstraction party. So we can use basically whatever people are building for account abstractions currently. But we have a lot of open discussions. We have a lot of details, and we have a lot of things that we are researching currently because, well, our idea is not simply moving ZK login to Ethereum is actually improving on it and, well, doing it at the same time. So the first big problem is that we're relying a lot on the OpenID provider. Because if the OAuth account is lost somehow, like if you lose control of your account, if Google, for example, bans the user, they will not be able to sign transactions anymore. They won't be able to update their ephemeral key. And this comes directly from like our initial assumptions, but this is not cool. Also, proving is very heavy work, as I was saying, right? We have to do SHA-2. This is not snark-friendly. We need a very beefy machine. And the user actually has to reveal their JWT to the prover. So is there any way we can locally prove this? Is there any way we can make sure the prover is not leaking this? Also, we really need to think about a way of fetching JW keys on-chain. Sui does this from their nodes, but we need a way of making, well, a smart contract-based Oracle or something that will provide this data for us. And we also need to think about how to deal with salt. Because as I mentioned, you have the salt. It's now unlinkable to your original identity or your ZK login address. But we don't want to make the user deal with that at the same time that it's a trust point, if you think about it, or a privacy preserving problem if you're making a service that deals with this or that stores this. Because if they have salt, then they will be able to link a user with their Web2 identity. So in terms of prover services and local proving. Again, the problem is, well, very hardware intensive. People are forced to send their identity data. We wouldn't like that. So 2 ways we could go around this. One of them is, well, let's make ZK go faster. Recent developments on ZK proving, we could test this out. We can try to get some performance improvements there and see how far we can get. It's still a very non-ZK friendly thing, right? So we have some other options that are not really into the ZK complexities. One of them is, well, instead of trying to make this local, let's try and make the salt private. One option for that would be, let's run the prover through TE. Right, we have TDX now, so performance should be a little bit better. I don't know. We can make sure that the prover doesn't reveal the private inputs through TE. We get attestations and everything, and we trust those attestations. That is an option. We could also use MPC. So we have a network of provers, and we just assume there will be no collisions. Another point of research, well, how do we get JW keys? We really need these JW keys in order to validate the JWTs, and it would be good that those are rotated whenever they are changing in a trustless way. It's very easy to identify if they're not, but still, we don't want to rely, for example, on a governance protocol. So we could use something like TLS Notary. That would be an interesting solution. TLS Notary, town crier, solutions of the sort. And then we can prove that the API call to the OpenID provider was done correctly and that those are DJWTs. That would be very nice. We could do that. On salt services, well, again, we can't make the salt public. We want to make it trustless at the same time. Aptos Keyless has a similar solution to ZK Login, by the way, and they have some interesting proposals. On their case, it's Pepper, the way they call it, but it's essentially, it's a similar working in this sense. I'm not going too deep into them because they're a little bit more complex. I'm bringing some other solutions here, which are, well, again, TE or MPC. The intersection between them are quite high, right? Again, you can use TE. You can prove that your program is the one that you expect and that it's not leaking your salt anywhere. You could use MPC and, well, collusion considerations. But one thing I would also like to bring is that, differently from the prover, we have an additional concern here, which is availability. Because if the salt service is not responsive anymore, we have a real problem. The user needs to get their salt in order to make transactions. So we also need to think about a way of this being, well, TE and MPC in terms of privacy solutions are lower-hanging fruits, but availability is a larger issue, and we need to think, well, distributed system maybe, that could be a solution. And another thing, well, from the first open question that I mentioned before was, we need a recovery process. We don't want the user to lose their account in the case that they are banned from their OpenID provider. But This is actually like probably the hardest question of them all in a general sense, because it requires more. It's less technical in the sense. It could be said like that, because recovery process options are basically similar to any other account abstraction application. So you can have like social recovery, you can have different approaches, but there's not such a thing that can be seen that is specific to ZK login in this case. Though there is a little bit of a different way to look at things. Well, we could also bring ZK login as a recovery process to account abstraction. So whenever you're setting your account, your smart account, you just say, OK, here's my identity through my ZK proof. You store it there, and you make some parameter like, OK, if I'm idle for a month, then that means I probably lost my private key or something. So we could use my OpenID attestation to get my account back. This way, you're not relying too much on your OpenID provider to make transactions. But like this is less of a convenience. This is more of a security feature now. So it's a different way to look at the same problem, more or less. And well, that's basically it. All of the questions. We have a clear outline of what we could do, but there are lots of things, lots of details that we need to iron out and to think about it in a better way. So yeah, let's build together. Feel free to get into contact if that's something that interests you and that you want to discuss. We would be happy to hear from you all. Thanks a lot.